Welcome, everyone, to the North Atlantic Fire Science Exchange's Fall 2025 Student Webinar Series. My name is Eric Evanson, and I'm NAVSE's Science Communications Specialist. Now, the goal of the Student Webinar Series is to connect students with the fire and forestry community to develop positive working relationships, as well as exchanging knowledge. And speaking of exchanging knowledge, just kind of want to remind everybody that NAVSE is part of the Joint Fire Science Program's Fire Science Exchange Network. There's 15 exchanges in all. You can see them there on the map. And if you would like to learn more about any of the exchanges or the Joint Fire Science Program itself, I would encourage you to go to firescience.gov. Now, today's talk is entitled A Likely Pyrophyte, Moisture Content, Growth Allocation, and Thermal Resistance of American Chestnut Bark Resembles Fire-Tolerant Species. And our speaker today is Niesz Kutsch from SUNY ESF. And the way the presentation will go is Maya will begin first, and then we'll follow up at the very end with a question and answer session. Now, if any time during the presentation you have a question, feel free to pop that into the chat. And again, we'll revisit that at the very end. And then we'll follow up at the final with some closing thoughts for the Fall 2025 Student Webinar Series season. And with that, I'm going to go ahead and stop sharing my screen, and I'm going to invite Maya on to share her screen and give us a little bit of a background about herself before she starts her presentation.
Hey, hello everybody. My name is Niesz Kutsch, and I'm really happy to be here. Thank you so much for having me. A little background about me. I am a master's student who is just about to defend here at SUNY ESF. I am getting my degree in plant science with and I finished my bachelor's degree a few years ago with a degree in botany from Kent State University. So I'm definitely more on the plant-focused side, but I was really happy with the opportunity that I got in my master's degree to learn about the interactions between plants and fire. So this talk is going to be pretty specific on plant traits that relate to fire tolerance of the American chestnut. So with that, I'll get into it. There we go. So first, to introduce the American chestnut, or the scientific name Castanea dentata. It was once one of the most common trees in our eastern forests. It was an important foundational species, and in places where it was dominant, it would be often up to 1/2 of all the biomass in the forest there. It produces burrs which contain 3 nuts each, and these nuts are very nutritious and dense. And this also has a very tall, straight growth form. These trees would become very large. And it was, very common in the Appalachian Mountains. So you can see here on the left, all of this white haze shows where the chestnut trees were when they were in bloom. They have these very large, white, fragrant flowers that produce a lot of pollen. And a lot of insects feed on this pollen. And there were many species that were evolved specifically to feed on the American chestnut. Multiple species of moths, many of which are now extinct, sadly, and also bees like the chestnut bee, which is actually recently rediscovered in New York State. So that was a really exciting moment that brings, some hope that we may see some of these species return. But yeah, like I mentioned too, other than being a food source for insects, it's also, the nuts are a very large food source for many animals. They could be relied upon yearly in a yearly mast, unlike most other nut-bearing trees, which may mast like every other year or even more infrequently and hard to predict. But this was a very regular food source that could be relied upon. And of course, humans also enjoy these nuts. They're very tasty. And the American chestnut was a very important tree for humans with the nuts and with the wood that I mentioned. It's a very rot-resistant, high-quality wood. But as you've noticed, I've been talking about this tree a lot, kind of in the past tense. This is because, although it was once very common, it is now considered functionally extinct. And this is due to the chestnut blight, which arrived in the Americas in the late 1800s, early 1900s, and was discovered in 1904 in the Bronx Zoo, actually. This chestnut blight swept through the population and killed out basically all of the trees in a matter of decades, which on this continental scale, that is very fast. However, the trees are still in our forests because the blight kills the tops of the trees, but it doesn't kill the root system. And these chestnut trees are actually very good at resprouting from the roots. And this has allowed them to survive and not become actually extinct and only functionally extinct. So these trees have survived by resprouting from the roots. However, after just a few years, the blight will find them again and kill them back down to the roots. And so that's kind of been the state of the American chestnut for the past 100 years. This just cycle of dying and resprouting and dying and resprouting, but not being able to grow large enough to flower and reproduce. However, this is where the lab that I work in comes into the picture. The lab that I'm in, which is called the American Chestnut Research and Restoration Project at SUNY ESF, the researchers in the lab have developed transgenic American chestnuts, which have one gene added that allows them to break down the toxin that is produced by the chestnut blight, or the fungus that causes the chestnut blight, rather. It is called oxalate oxidase, which means it is an enzyme that breaks down oxalic acid, one of the main weapons of the fungus. And this allows the trees to resist the blight. So that way they will still get the blight. However, the blight will not kill them in most situations. And so the trees can grow larger and they can grow large enough to reproduce. And through this, restoration of these very important trees is on the horizon. And then so that's where my research comes in, is that now that restoration is coming, we're looking more at learning more about the ecology of the American chestnut. So that way, when we do restore them, we are able to do it with the most success off the bat in establishment success, and in that type of deal. So what I specifically am researching or talking to you about today is the relationship between American chestnuts and fire. Because they have been absent from our forest for so long, we don't really know the relationship between American chestnuts and fire. But as I'm sure all of you know, fire can be a very important tool for restoration and management. And that many species of plants are adapted to fire, and without fire, they also disappear from the landscape. And there are multiple different strategies of fire adaptation that plants can have. Two contrasting ones that I'll highlight here are recovery and resistance. A tree, or a plant species, but in this case a tree, that has a recovery strategy may be top killed or burned down to the roots by fire. However, they have the capacity to resprout from the roots and come back very strong after a fire. Whereas on the resistance side, the tree may just have thick enough bark that once it reaches a certain size, it is able to just resist and continue as normal when the average surface fire comes through. And so I believe that the American chestnut may be fire tolerant for multiple reasons, and that in many cases it may take more of that recovery strategy. Because with the resprouting that allowed it to survive the blight and not become extinct, that may be an adaptation that it was originally meant to survive either high uh, browsing or fire. And we see this resprouting trait very strongly in a lot of species that are fire tolerant. This ability to really quickly resprout and quickly grow and take that opportunity of increased light and nutrients and reduced competition and really take advantage of that. Um, on the left here, we have an overlay of the natural range of the American chestnut with the dotted lines. I don't know if you can see my cursor, but you can see the dotted lines. That's the range of the American chestnut, the original range. And the colors represent the mean fire interval. I'm sure a lot of you are probably familiar with this graph or ones like it that show fire intervals. But the important takeaway is that in over 80% of the American chestnut's natural range, it would have been receiving fire at least every 12 years or more frequently, which you can recognize that on the lifespan of a tree, that is a significant recurrence of fire that the trees would have to be able to survive to be in an established stand there. Going back to more traits that are associated with fire tolerance that the American chestnut also has, um, it has been shown that they have highly flammable leaves, which is really interesting, and a lot of people don't think about it, but many species that are fire tolerant have very flammable leaves because they kind of want to encourage fire and encourage that habitat that they do best in. And American chestnut happens to have very flammable leaves, which suggests that they're fire tolerant. And there are, a few different traits that kind of, suggest that, but nothing has really shown that they do survive and like fire. So I wanted to delve a bit more specifically into some traits that we haven't really considered of the American chestnut and how it relates to fire. And so I looked at the bark traits of the American chestnut. Bark trait or bark traits are definitely linked to fire tolerance. One main one is bark thickness. You can imagine that the thicker the bark is, the more insulative capacity it will have to protect the inner growing cambium from death by heat. It's acting as insulation. So the thicker the bark of a species, the more likely it will be fire tolerant. So I wanted to quantify both the bark thickness, but also the insulative capacity of American chestnut bark. For example, there's other traits too that are involved. For example, the moisture content. A higher moisture content will also help increase that insulative capacity. And I also just wanted to do a direct heating experiment to just specifically see the time it would take to cause the beneath the bark to raise to a lethal temperature and compare it to different species. So how I went about this was we tested the American chestnut and also the Chinese chestnut, which has implications for restoration, and we wanted to see if there were differences between these two species. And we also tested white oak, which would be our fire tolerant representative, and our red maple, which would be our fire intolerant representative. I was also sampling very small trees that were less than an inch in diameter at the root collar, because at this size class you see the most differences between species in their ability to survive a surface fire. I predicted that the American chestnut would be more on the fire tolerant side, but maybe not so extreme as white oak, and that Chinese chestnut would be less fire tolerant, because in its native range, it is a more mesic or wet habitat, and that it would look more like the red maple, which is highly not fire tolerant. I also expected to see increasing bark thickness with increasing fire tolerance of the species. So then for this heat exposure experiment, which I would directly see how long it would take for the bark to heat up to a lethal temperature of each of these species, what I would first do is I would slice the bark off of the tree. I took it from 10 centimeters above the root collar, and I made sure to cut deep enough into the tree that I also took some wood off the tree. That would make sure I got the entire bark profile. And then I would peel that piece of wood off of the bark. And then I brought it into the lab, and then I made my sandwich. There's a bunch of layers here that went into preparing each sample to be heat tested. The first one is a wooden dowel. This was used as the rounded form of the dowel would mirror the rounded form of the bark. Because if I press the bark flat, it would crack, and obviously then that would not be representative of the actual bark on the tree. You know, the cracks would let air and heat through much faster. So we started with a wooden dowel, and then I placed a thermocouple, which would tell me in real time the temperature that the thermocouple was reading. And then on top of that went the bark sample. And then around the edges, I formed a clay seal to make sure that no hot air would be able to seep under the bark, and any heat would have to go through the bark to heat up the thermocouple. On top of that, we placed a reflective foil to reduce the amount of heat that the clay would be absorbing. And then our sandwich was ready, and we put it under a heat gun. So the heat gun would release heat at a regular temperature at a regular distance from the sample. So that way this would be the same across all the samples, and we could compare them. And we just turned the heat gun on until the sample or the thermocouple read 60 degrees Celsius, which is 60 degrees, 60 degrees Celsius, which is the lethal temperature as used in literature for the vascular cambium within a tree. So there's the thermocouple and there's the sample. And we just saw how long it would take for each sample to heat up to a lethal temperature. Here's some photos of this in action. You can see with the clay and then the reflective foil on top, the heat gun. But before we get into the results from this testing, I also just took some measurements of the bark traits of all the samples. For one, I measured the bark thickness, and I also had measured the diameter at the root collar of each of the trees. From this, I could calculate a bark allocation ratio, or how much of the diameter of the tree was made up of bark. The higher this was, the more the tree was investing in its bark and the bark thickness. I also recorded the bark moisture content, as this would show how high the moisture content was. I did this by placing the bark samples in a dehydrator, and I measured the weight of the samples before and after to calculate how much weight they lost as they dried out. And from this, I could calculate the moisture content of the bark. And like I said earlier, the higher this is, the more likely the tree is investing in fire tolerance. And this is because the more moisture, the more heat has to go into the phase change of that water from liquid to gas before it can travel further into the bark. So here are the results of these traits. The first one, this shows the relationship between bark thickness and an increasing root collar diameter by each species. you can see that the American chestnut and the Chinese chestnut have a pretty steep slope. And also oh, I think this is the, oops. This is actually the wrong graph for this. I apologize. So actually ignore this graph for a second, please. I'm sorry. Yeah, this one is correct though. So this graph shows the bark allocation ratio, or the percentage of the diameter that was bark as the root collar diameter increased. You can see that for the chestnuts, they both the bark allocation ratio stayed steady, and it stayed around 15%, which is not the highest that you see out there, but however, that is pretty significant, especially when you contrast it to the red maple, which started at around 8% and then went down below 5%, which makes a lot of sense, as red maple had very thin bark that did not really get thicker even as the tree was growing thicker. So there was a clear difference between the red maple and the chestnuts in their bark allocation. The white oak is a bit of an interesting case. We had some sampling issues. We actually did 2 rounds of testing, one in the fall and one in the spring. And then we had issues sourcing more white oak in the spring, so we had to unfortunately use samples that had to be shipped to us, and in the shipping, or just because they were from a different population, they had some just different bark traits. So the white oaks are a bit weird, unfortunately. But you can see in the first fall group that we sampled from, they had the highest bark allocation out of anything we tested, averaging, between 15 and 20%, with some samples even reaching up to like 24%. The spring samples, however, were lower, around 10%. But this graph shows that the chestnuts are definitely investing in their bark and in thicker bark. Then this graph shows the moisture content of the bark samples between the fall and the spring samples. The letters above each box and whisker plot show statistically which groups are the same. So each box and whisker plot that has the same letter as a different group, they are not statistically different. When there are different letters, they are statistically different. So in the fall, both the American chestnuts, Chinese chestnuts, and white oaks all looked the same. They're all statistically the same. Whereas they contrasted from the red maple, which had significantly less percent moisture. In the spring, we saw each species increase in the percent moisture of their bark, probably because it was a very wet spring and the sap was flowing and there was water just on the surface of the bark, that we were unable to really remove without messing with the validity of the experiment. However, the one that breaks this pattern is the white oaks, which had to be, like I said, shipped in. And so in shipping, they may have dried out. But it is still shows us that the American chestnut and Chinese chestnut have a very high percent moisture of their bark, whether it is fall or spring, and it is significantly higher than the red maple. And even in this case, higher than the white oak. And so the more moisture in the bark, the more energy that has to go towards this phase change that's not going further into the tree, and further towards girdling the tree with heat damage. And now getting into the heating data, which is really exciting. So this graph does show the time to lethal temperature by the root collar diameter of each tree. And you can see once again, the chestnuts, they both have a strongly positive slope, which is showing that as the trees were growing larger, they were taking more time to kill. And the overall times that we were seeing for these species anyways, were higher than the other species. So for example, if you have a tree that is 20 millimeters thick at the root collar, an American chestnut may be able to survive a mild surface fire for around like 100 seconds. However, once that tree is up to 40 millimeters thick, it'll survive for at least 200 seconds, which, you know, in the times that a mild surface fire is going through a forest, oftentimes that is only, you know, taking a couple minutes. So it is likely that an American chestnut that is at least 40 millimeters thick at the base of the tree very well may survive that fire, which is really exciting to see and really interesting. The Chinese chestnut slope was also not significantly different from the American chestnut slope, which we really saw throughout all of our results. The American and Chinese chestnuts looked very, very, very similar, which is just very interesting. And it shows that Chinese chestnut trees may also be fire tolerant, and they may be able to be used before you can plant in American chestnuts to help prepare a site for a new fire regime that may also be beneficial for once the American chestnuts are there. The red maple, they did also take, you know, at least 100 seconds before lethal temperature. However, they had a much shallower slope, and trees that are 40 millimeters thick would be reaching lethal temperatures in like 150 seconds, which the slope was statistically different than the chestnuts. So this was really exciting to see, that even as the trees are getting bigger, their increase in insulation of the bark is increasing a lot more slowly. The white oaks actually had the shallowest slope, which was, you know, completely not what we were expecting to see from the white oaks. However, once again, this might have just been due to the shipping issues. The fall round of sampling of white oak actually had the initial starting highest insulative capacity. However, then it's just those spring samples are then so much lower. So in another experiment that is able to use the same white oaks throughout, even as they're getting larger, they may see a different pattern. But still, we had very clear responses from the American chestnut and the Chinese chestnut that they are rapidly increasing their ability to survive a mild surface fire. This graph shows the same results, but instead of looking at it as instead of looking at it as the diameter of the root collar of the tree gets larger, we're looking at it as the bark thickness increases. And that leads to a really weird looking graph, because specifically for the red maple, the bark never did really get thicker. The bark thickness stayed, you know, right around 1 millimeter thick. And for the white oak, we also saw a more limited range of bark thicknesses. But this graph does show you that as the American and Chinese chestnut trees grew larger, their bark was also getting thicker, and which shows us that then as a result, it's also increasing the time to lethal temperature. What is interesting to me about this graph, though, is that it shows that with the red maple, the increase that they had in time to lethal temperature could not be attributed to increasing bark thickness. Therefore, I think that their increase in time to lethal temperature may have been due to that increased moisture content. So for them, it may be more of a factor of the seasonality rather than the trees growing larger. So I think this experiment would be really interesting to do again with a range of tree sizes that are all sampled at once. So that way you can remove that seasonal difference. I would also be really interested in doing this experiment again with a consistent group of white oak samples. The difficulty in finding these saplings of white oak is actually kind of a commentary too on how important this research is. One of my advisors, Dr. Van der Yacht, has done a lot of research or has a deep understanding of mesification, which is the process that we are seeing in a lot of our forests where they are transitioning from a community of plants that kind of cultivates this drier, more fire-prone xeric habitat is being replaced by a lot of mesic species, which promote wetter, cooler conditions. So basically, we're losing a lot of our white oaks, and the regeneration that we're seeing in these forests is maples instead of regenerating oaks, and it is changing the conditions of these forests. And it's really hard to kind of undo without a lot of work. And I kind of encountered this in my own research because I couldn't find any regenerating white oak, which was really unfortunate. So I think doing this experiment again, with a larger availability of white oak would be really interesting. But also that my results also show that the heat gun method does give you clear results, and I think that this method could be definitely used again, and there's opportunities to refine this method even further so it can be more reliable. But in conclusion, both the chestnut species really looked the same. And the chestnuts definitely demonstrated fire tolerance traits exceeding red maple, for sure. And in our results, it also looked like they exceeded white oak. However, this may have just been due to the sampling issues. We can't really say. And that's why I would love to do this experiment again. However, my results do support that the American chestnuts have bark traits that align with fire-tolerant species. More research should definitely be done with directly putting actual fire on American chestnuts, and some of my colleagues at ESF are actually doing this. For example, with the research of Mariah Luron, she is doing some projects putting fire on actual chestnuts, which is really exciting. Definitely more of that should happen in the future. However, this research definitely informs restoration best practices. Surface fires could be used for pest management in chestnut orchards to, for example, reduce occurrences of chestnut weevil. It could also be used for invasive species management and for improved establishment of trees in restoration plantings. Even if these seedling chestnut trees are burned to the ground, they do have the capacity to resprout even at this small size. So if you do a burn, it will likely kill the maples off, which then when the chestnuts resprout, they will have much more availability of light and nutrients to really take advantage of, and they will likely really shoot up and be able to establish well. Another thing, I often get this question of could we maybe use fire to kind of, kill off the chestnut blight off of chestnut trees. Unfortunately, that is probably not a viable strategy, because the chestnut blight kind of gets into the chestnut trees on any scars or like it could land in crooks of branches and stuff. So fire will probably cause more scars on trees, which then gives more opportunities for chestnut blight to enter. So that is probably likely not helpful. Um, but yeah, fire could definitely be used as a restoration management tool in restoration chestnut plantings, which is really exciting. Um, and that is my presentation. Thank you so much for listening. And I would love to take any questions people have now.
Well, thank you very much, Maya. I think we may have seen your cat in the background actually there. Oh,
Yes, yeah. I've got actually have eyes on all three of the animals right now. They really love to hang out with me, which is really nice. Yeah.
perfect.
I can bring
Yeah,
her up right.
thank you for your presentation. I've got a couple quick questions. If anyone else has any questions, now is a great time to pop those into the chat, and we'll get those answered. So my first question for you is, so the restoration efforts that you're doing there in the lab, are there any other restoration efforts going on in other states, or are you the only folks working on this right now?
Yeah, so there are a few different organizations that are taking different strategies to chestnut restoration. There have been many different strategies taken over the past 100 years since this has been an issue. Um, Other organizations are pursuing back cross breeding programs where they are um, trying to basically breed the resistance of Chinese chestnuts, which are naturally resistant to the blight because they co-evolved alongside each other. Um, so they are trying to do back cross breeding programs to kind of breed the resistance of the Chinese chestnut into the American chestnut. Um, However, this is kind of proved a bit difficult because the resistance in Chinese chestnut is due to a suite of genetics, which is hard to isolate. However, they're definitely working on that, and it is very important to take, multiple routes towards restoration, because different routes will be, more suited to different situations. Um, I do believe we collaborate with some other research labs in different universities. I unfortunately can't remember them off the top of my head right now. Um, but I believe we are the only lab who has developed the transgenic chestnuts. And the other labs we are working with are kind of working with the chestnuts we have developed, I believe. But yeah, there's a lot of good work going on, for sure.
Okay, great. And then one other quick one. So when you were talking about slicing the bark off the trees, where was that all done in New York State then? And then you were talking about like white oak being kind of shipped in. Where were you getting the white oak from? And does that matter in these experiments?
Totally. That is a great question that I totally skipped over. Thank you. So, I sampled in the first round of sampling in fall. Everything was sampled from one of our field stations. It's called the Lafayette Experimental Station. It's about 15 minutes south of ESF's campus in Syracuse. Um, and in the spring, I got um, oh, yeah, and a bit more detail about that. Both the chestnut species were sampled from our orchard plots. The white oak was sampled from potted seedlings that had been purchased the previous year. And the red oak, or excuse me, red maple rather, was sampled from a forested portion of the experimental station. Um, and so then in the spring, the chestnuts and the red maple were sampled from the same locations, different individuals, um, but the same locations. However, I had already sampled all of the white oaks that had been, you know, bought and potted up. They were all the same size, so I couldn't get any larger ones. So I looked around the region for natural white oak regeneration, and I couldn't find any from the sites I had been kind of told to check. I actually last week I happened to go to Cicero Swamp, and there was actually a lot of white oak regeneration there of like the perfect size. So it's really unfortunate I didn't know about that location earlier. Um, but so what we ended up doing was my advisor, Dr. Newhouse, had a contact at with the with Sky Vanderlaan, who works at the Albany Pine Bush in the Albany Pine Barrens. And they had a lot of white oak regeneration there because of the uh burning work that they do there to sustain their unique pine barren ecosystem. So she sampled for me very generously and shipped the samples to us. Uh She did ship them, like, using, like, 2-day shipping, however, there was just some issue where they took longer to reach us, and so I believe that the results we saw with the white oak were due to, the samples drying out during shipping. There is also a chance that it is just because of the different genotypes of the different areas, just causing, you know, a different investment in bark thickness or that type of thing. Um, I believe it is mostly due to them drying out and thus, like, thinning, during shipping.
Got it. All right. Thank you. I think I saw, I think I saw Neil pop in that they've got some white oak over there in the Albany Pine Barrens. But a question for you here from the chat. Can you describe approximate ages or height of your study saplings?
Totally. Um, so the, white oaks that were potted up were about, um, between, like, 18 inches and maybe, like, 2 feet tall, um, and they were probably, like, generally around, like, half an inch thick in diameter at the root collar. Um So they were probably just like 1 to 2 year old seedlings. Uh, the red maple, because it was in a forested setting, which this is definitely um, it's, you know, something to talk about in regards to the study to help people understand maybe some of the differences. The red maple were also the same thickness, however, they were um, due to them being in a like forest situation. They were, much taller, like 5 or 6 feet tall. Um, so they, you know, I don't know how old they were, but they were, um, you know, much taller and thinner, because they were really, like, shooting up towards that light. Um, the, chestnuts were, I would say, were much more similar to the red maple, that they were, you know, the same thickness, however, they were, you know, 5 or 6 feet tall, shoots. A lot of them were, like, basal resprouts or, just basal sprouts off of larger trees. So yeah.
Excellent. All right. Thank you for that
Mhm.
response. And then I'll make sure I got a thumbs up for you on that question there. And then I'll make sure Polly put in a comment about some of the chestnut out on Long Island and a name for you. And I'll make sure you get that information to be able to connect up with that individual out there. Are there any more questions that somebody wants to put in the chat? All right. Then Maya, if you want to stop sharing your screen, and I will share my screen here.
Um, there we go.
There you go. All right, let me share one last thing here. All right, so just kind of wanted to mention to everybody, this was the our final talk of the fall 2025 student webinar series, but there is good news as we do have a spring 2026 session planned. We already have a couple of speakers, but we're always looking for more. So if you or someone you know has a project that they'd like to share in this format, feel free to reach out to me. You can see on the screen there, Eric Evanson at nafchelp@gmail.com. And if you want to learn more about the student webinar series or see any of the past sessions, because this is being recorded, you can go to firesciencenorthatlantic.org, our website, and go to our student webinar series page, or you can hit up the QR code there and get directly to that student webinar session page. Last thing I kind of wanted to mention is that when you do close your browser from this session, a very brief survey pops up, 4 simple questions. If you could just take a quick minute to fill that out, we would greatly appreciate that. Otherwise, just wanted to thank you again, Maya, for your informative talk today. We really appreciate it. And I wanted to thank all of you for joining today as well. We'll go ahead and keep the session open for another minute or two in case there's any last minute questions that pops into people's minds. Otherwise, thank you again, everybody, and have a great day.